Right now, two spacecraft continue to send news from a point no human-made object has ever reached before. These vehicles left behind a boundary where our star's protective wind dies out, where the temperature spikes to 400,000 degrees, where hydrogen walls press in from every direction, and where radiation levels instantly triple. This is the edge of our solar system, and the deeper we look, the stranger the picture that greets us. Before we get into it, don't forget to like and subscribe. In 1977, two spacecraft left Earth for a mission planned to last only 4 years. The mission of these vehicles, named Voyager 1 and Voyager 2, was simple: fly past Jupiter and Saturn, take photographs, collect data, and then fade into silence. Nobody had predicted they would survive this long. Nobody thought they would still be transmitting signals nearly 50 years later. And certainly nobody had foreseen what they would encounter at the edge of our solar system. For decades, these two machines drifted ever further from home. They flew past giant planets, they crossed the orbits of icy worlds, they entered distant regions where it takes hours for our star's light to arrive. Then, one by one, they began to notice something strange. The environment around them was changing. It wasn't a dramatic explosion or a visible wall. At first, it was extremely subtle. The instruments on the vehicles began recording shifts in particle density. The solar wind, the stream of charged particles flowing outward from our star, was behaving differently. It was slowing down, heating up, and colliding with something. Scientists on Earth, watching the data come in, realized the Voyagers were approaching a boundary. It wasn't a tangible physical barrier, it was a transition zone where our star's influence was beginning to fade, and the influence of interstellar space was beginning to take over. This boundary has a name: the termination shock. You can compare it to a river meeting the ocean. The river doesn't stop abruptly. It collides with the larger body of water, and that collision creates turbulence, mixing, and chaos. At the termination shock, exactly this happens. The solar wind, traveling outward at over 1.6 million kilometers per hour, slams into the pressure of interstellar space and suddenly drops far below its original speed. Voyager 1 crossed this boundary in 2004 and Voyager 2 in 2007. Both vehicles confirmed something scientists had only theorized. The edge was real, it was measurable, and it was violent.
So where do things get unsettling? When the Voyagers crossed the termination shock, they didn't find what the models had predicted. Temperature readings were inconsistent. Magnetic field data was confusing. Particle counts didn't match expectations. Scientists had been building simulations of this region for decades, yet the reality turned out to be far more complex. Why does this matter? Because the termination shock is the first line of defense between our solar system and the rest of the galaxy. Everything inside this boundary is shaped by our star's energy, while everything outside is molded by forces we don't yet fully understand. Until the Voyagers crossed this boundary, we had no direct evidence of what this transition actually looked like. Now we do, but it raised more questions than it answered. The data revealed that the termination shock is not a fixed, neat line. It wobbles, it shifts, moving closer to and further from our star depending on the activity level of the solar wind. In some years, it may sit 13 billion kilometers away, while in others it can pull back to as far as 16 billion kilometers. The edge is not static, it breathes. And that breathing is being influenced by something pushing back from the outside. This gives us the first sign that interstellar space is not passive. It's not an empty void waiting beyond our star's reach. It's an active environment with its own pressure, its own particles, and its own magnetic fields. And it is constantly pressing inward, testing the strength of our star's protective bubble. The Voyagers taught us this. We live inside a fragile, invisible cocoon inflated by our star's energy. Outside that cocoon is something else, something older, colder, and waiting there for billions of years. But crossing the termination shock was only the beginning, because what the Voyagers found after that made even less sense. The further you travel from our star, the cooler everything should get. That is basic physics. The further you move from a heat source, the less energy reaches you. By the time you reach the outer solar system, temperatures drop far below zero. Space becomes cold beyond imagination. Yet at the termination shock, the temperature suddenly spikes to 400,000 degrees. This is not an error, nor a sensor malfunction. Both Voyager vehicles recorded it, completely overturning the expectations of scientists.
To understand this, we need to rethink what temperature means in space. On Earth, when we talk about temperature, we generally mean how hot or cold something feels to the touch. But in space, there are almost no molecules. Regions near the termination shock contain roughly only 1 particle per cubic centimeter. Compare that to the air you are breathing right now. In that same space, there are billions upon trillions of particles. So even though the individual particles near the termination shock move at extreme speeds, which is what temperature measures, there are so few of them that you would feel no heat at all. While your skin would still freeze, the particles themselves could be vibrating with the energy of a furnace. This is one of the strangest paradoxes in our solar system, a place that is simultaneously superheated and freezing cold. But this discovery doesn't just satisfy scientific curiosity, it matters for a very practical reason as well. The termination shock is where the protection begins to weaken. Inside this boundary, the solar wind reigns. It sweeps away dangerous particles coming from deep space and creates a pressure that holds back the interstellar medium. At the termination shock, however, that pressure drops, the wind slows, and the barrier thins. This makes it easier for radiation coming from outside our solar system to seep in. Scientists confirmed this by comparing data gathered from inside and outside the termination shock. Cosmic rays, high-energy particles from exploding stars and black holes in distant galaxies, increased noticeably the moment the Voyagers crossed this region. The protective bubble could no longer hold them back as effectively as before. For humans, this is critical information. Any spacecraft traveling toward the edge of our solar system will have to pass through this region. The astronauts inside will be exposed to increasing radiation in the very zone where temperatures spike. Shields that account for both particle energy and rising cosmic radiation will be required. We are only just beginning to understand what this transition zone demands.
Picture the termination shock, a river that begins at our star, whose surface reaches millions of degrees and tears atoms apart into charged particles, and flows steadily outward for billions of kilometers. These particles, mostly protons and electrons, are hurled outward at incredible speeds. By the time they pass Earth, they are traveling at roughly 1.6 million kilometers per hour. This solar wind blows without pause. For decades, scientists wondered what would happen when this wind finally met resistance. It would have to stop eventually, but nobody knew exactly where or how. The Voyagers answered that question. As Voyager 1 crossed the termination shock in 2004, its instruments recorded a sudden and striking change. The speed of the solar wind dropped from over 1.6 million kilometers per hour to below 400,000 kilometers per hour over a relatively short distance. It was like a supersonic jet slamming into a thick wall of mud. This slowdown is violent. The particles don't stop gently. They pile up, compress, and collide with each other and with the slower-moving material ahead of them. The result is a turbulent, chaotic zone where energy is transferred in unpredictable ways.
But the unsettling part was this: the slowdown was not smooth. The Voyagers recorded fluctuations. The wind speed would drop, briefly recover, then drop again. The boundary itself was rippling and shifting. Scientists realized the termination shock is not a fixed wall. It expands and contracts depending on our star's activity level at any given moment. When our star is in an active phase, generating more flares and hurling out more material, the solar wind strengthens and pushes the termination shock outward, sometimes by hundreds of millions of kilometers. When the star quiets down, the wind weakens and the termination shock slides inward. The edge of our solar system is literally breathing. This creates a serious problem for anyone hoping to travel to this region. You cannot aim at a fixed point. The boundary you are trying to reach may have moved before you get there. And when you do cross it, the environment changes dramatically. The slowdown of the solar wind has real consequences for spacecraft. The charged particles that make up the wind create a kind of pressure around everything they pass through. When the wind slows, that pressure shifts. The forces acting on a spacecraft become unpredictable, and navigation becomes harder. But the more worrying consequence concerns what happens to the protection. The solar wind acts like a shield. As it blows outward at high speed, it sweeps away particles coming from deep space. When the wind slows at the termination shock, that shield weakens.
The moment the Voyagers crossed the boundary, they recorded an increase in cosmic ray density. These particles don't come from our star, they arrive from outside and in greater numbers because the wind is no longer strong enough to hold them back. For human health, cosmic rays are a serious concern. They can pierce spacecraft hulls, damage DNA, and increase the risk of cancer. Short-term exposure can be survived, but prolonged exposure, such as a multi-year mission to the outer solar system, could be fatal. Something is pressing against the edge of our solar system. Not a spacecraft, not an asteroid, not anything physically solid. It is a wall of hydrogen atoms that has been building up at our doorstep for as long as our star has existed. Both Voyagers detected it. Other instruments nearby did as well. For years, scientists debated what it actually was and where it came from. What we know for certain is this: as our solar system moves through the galaxy, it passes through the thin gas that fills interstellar space. This gas is predominantly hydrogen, the simplest and most abundant element in the universe. The atoms are spread incredibly sparsely, just a handful per cubic centimeter, but across vast distances, they accumulate into a significant amount of matter. When these hydrogen atoms encounter the edge of our solar system, something strange happens. They slow down, pile up, and form a dense region scientists call the hydrogen wall. You can compare it to snow building up in front of a moving car. The car pushes forward, the snow piles up, and similarly, as our solar system sweeps through space at roughly 720,000 kilometers per hour, it compresses the hydrogen ahead of it. The Voyagers detected this wall indirectly. Their ultraviolet instruments picked up a glow, pointing to the presence of excess hydrogen. When scientists analyzed the data, they realized the glow was too strong to be coming from ordinary interstellar gas. Something was concentrating the hydrogen. Subsequent observations from spacecraft like New Horizons confirmed the finding. The hydrogen wall was real. But the more interesting part is this: not all of the hydrogen in the wall comes from within. Some of it comes from within. As the solar wind reaches the outer solar system, it interacts with the incoming interstellar material. Protons from the solar wind can steal electrons from incoming hydrogen atoms. When this happens, the protons themselves turn into neutral hydrogen atoms. These neutrals are no longer affected by magnetic fields and drift off in strange directions, some heading back toward our star, others piling up at the boundary. The result is a mixing zone where solar material and interstellar material exchange particles and form a complex atomic soup. This matters because ultraviolet light coming from distant stars has to pass through this wall to reach our telescopes. If the wall is absorbing and scattering some of that light, what we observe is altered. It also matters for any spacecraft heading outward. The hydrogen wall is not dangerous in the conventional sense. The atoms don't move fast enough to cause damage on impact, but their presence affects the environment in subtle ways, interacting with solar wind particles, influencing the shape of the heliosphere, and signaling that the transition from the familiar to the unknown has begun. As Voyager 1 passed through this region, it was entering a zone where the dominant material no longer came from our star. The hydrogen it encountered was ancient. Some atoms had been drifting through the galaxy for billions of years, produced by stars that died before our solar system had even formed. Right now, you are inside a bubble of material created by our star, but pressing in from every direction is older material, waiting. And it gets stranger still, because the hydrogen wall is only the outer edge of something much larger. Between the termination shock and the true edge of our solar system stretches a zone of pure chaos. This region is called the heliosheath, and it resembles nothing scientists had expected. For decades, researchers had imagined it as a neat transition zone. The solar wind would gradually fade, the interstellar medium would gradually take over, and the boundary between them would form a smooth gradient. The Voyagers proved them completely wrong. When Voyager 1 entered the heliosheath in 2004, its magnetometer began recording something strange. The magnetic field was not uniform, not stable. It had been broken up into countless small bubbles, each roughly 160 million kilometers across, tumbling off in every direction. Imagine a bathtub filled with foam. Each bubble is separate, sealed, and pressing against its neighbors. Now picture that bathtub being billions of kilometers wide and the bubbles being made of magnetic force rather than soap. That is the heliosheath. This discovery shocked scientists. Their models had not predicted it. Their simulations had not shown it. The magnetic bubbles only emerged when real spacecraft flew through and sent back real measurements.
So why do these bubbles form? This has to do with our star's rotation. Our star rotates on its own axis roughly every 27 days. As it spins, its magnetic field spirals outward like water from a rotating sprinkler. By the time this magnetic field reaches the outer solar system, it has been twisted and folded in complex ways. In the heliosheath, the solar wind slows dramatically. The magnetic field lines that were stretched outward by the fast-moving wind suddenly pile up, fold back on themselves, and reconnect in strange configurations. The result, instead of a neatly organized field, is a foamy tangle of magnetic bubbles. This has real consequences for anything passing through it. Magnetic fields affect charged particles. Cosmic rays traveling at near light speed are deflected by magnetic fields. A neatly organized field can act like a shield, steering cosmic rays away from a spacecraft or planet. A chaotic, bubbly field cannot provide the same protection. Scientists now believe cosmic rays can hop from bubble to bubble and find their way through the heliosheath far more easily than they could through a solid barrier. This means the region's protective effect is weaker than we had hoped. For astronauts on a deep space mission, this is bad news. The heliosheath was expected to offer some degree of shielding. Instead, it may be behaving like a sieve, allowing dangerous radiation to seep through the gaps between bubbles. But the bubbles are not the only surprise. The heliosheath is also home to massive pressure waves. When our star releases a coronal mass ejection, a giant wave of plasma and magnetic field surges outward through the solar system. It eventually reaches the heliosheath and slams into the slower-moving material there.
Voyager 1 detected several of these pressure waves. Each one caused the magnetic field around the spacecraft to experience sudden jumps and fluctuations. Each one took months, even years to pass, and each one made it abundantly clear just how dynamic this region is. The heliosheath is not a quiet waiting room before interstellar space. It is an active, violent environment where energy from our star collides with energy from the galaxy. Something invisible is trying to kill you. Right now, as you read this, high-energy particles are streaming in from space at close to the speed of light. These are protons stripped from atoms by supernova explosions, nuclei forged in the cores of dying stars. They are cosmic rays, and they are everywhere. On Earth, you are protected. The planet's magnetic field deflects the vast majority of them, and the atmosphere absorbs the rest. But in space, outside the shelter of our planet, cosmic rays become one of the most lethal threats a human being can face. At the edge of the solar system, their density triples.
The Voyagers confirmed this as they moved into new regions. Cosmic ray detectors tracked incoming particles at every stage of the journey. Inside the termination shock, levels were manageable. In the heliosheath, they began to rise. But when the spacecraft crossed into true interstellar space, the numbers climbed dramatically. Voyager 1 recorded an increase of roughly 300% in cosmic ray density compared to what it had measured in the inner solar system. The protective bubble created by our star was no longer filtering them out. This is not a minor detail, it is a fundamental obstacle to human exploration. Cosmic rays are nothing like ordinary radiation. They carry enormous energy. A single cosmic ray particle can carry more energy than a ball thrown by a professional player, compressed into something smaller than an atom. When these particles strike a spacecraft hull, they don't simply bounce off, they pass straight through, shattering atoms in their path. When they hit living tissue, they damage cells, break DNA strands, and raise the risk of cancer, neurological damage, and other health problems. The heliosphere acts as a partial shield. It cannot stop all cosmic rays, but it slows and deflects the great majority of them. Once you leave the heliosphere, that shield disappears. This is why the Voyager measurements are so critical. Before real data, scientists could only estimate. Now we know, and it is worse than some optimistic projections had suggested. Any crewed mission to the outer solar system would require radiation shielding of an unprecedented scale. Current spacecraft are not built to withstand this level of exposure over such a long period. Materials capable of blocking cosmic rays are heavy and expensive. Water, polyethylene, and certain metals can help, but you would need to surround the entire crew compartment with thick layers. That means mass. Mass requires more fuel. More fuel demands larger rockets. The engineering challenges multiply rapidly. And shielding is not even a perfect solution. Some cosmic rays are so energetic that nothing realistic can stop them. They punch through meters of material. The only defense against these is to limit exposure time. This creates a grim equation. The further you travel from our star, the weaker the natural shield and the longer the mission. You cannot outrun it by going faster because we don't have engines capable of reaching the necessary speeds. Voyager 1 did not cross the edge of the solar system once, it crossed it multiple times. This is one of the strangest discoveries of the entire mission. Scientists had expected the heliopause, the boundary where the solar wind stops and interstellar space begins, to be a clean transition. Inside, outside, and the crossing would happen once, permanently. That is not what happened. In the months leading up to the official crossing in 2012, Voyager 1's instruments recorded a series of strange fluctuations. The spacecraft would detect a sudden drop in solar particles and a spike in cosmic rays, suggesting it had entered interstellar space. Then, within hours or days, the readings would reverse. Solar particles would return, cosmic rays would drop. It was as though the spacecraft had slipped back inside the bubble. This happened several times before the final crossing. Scientists came to understand that the heliopause is not a rigid wall. It behaves more like a membrane, constantly moving in response to the pressure on either side. When the solar wind strengthens, the membrane pushes outward. When interstellar pressure increases, it squeezes inward. Voyager 1 arrived during a period of particular instability and experienced the boundary shifting back and forth around its own position. You can compare it to standing at the waterline on a beach. Sometimes a wave wets your feet, sometimes the water pulls back. You are not moving, but the boundary between wet and dry is constantly shifting around you. For the scientists tracking Voyager 1, this was both thrilling and frustrating. They wanted a clean moment they could officially announce. They wanted to say that on a specific date, the spacecraft had formally left the solar system. But the data kept coming back contradictory. Eventually, they settled on August 25, 2012 as the official crossing date. On that day, the solar particle count dropped permanently, and the cosmic ray count stayed high. The spacecraft had finally pushed through the last tremors of the membrane and entered true interstellar space. But these fluctuations raised important questions. If the heliopause is unstable, what does that mean for long-term protection? Could there be moments when the bubble shrinks dramatically, leaving the outer planets exposed to higher radiation? Could a sufficiently powerful interstellar pressure wave push the boundary significantly inward? Scientists believe the answer to both questions is yes. Looking at geological timescales, the heliosphere has almost certainly changed in size. When our star was younger and more active, the bubble was probably larger. When passing through denser regions of interstellar gas, the bubble compresses. There may have been periods in Earth's history when the edge of the outer solar system was much closer than it is today. This could have affected life on our planet. It may have altered the climate, since high cosmic ray levels have been linked to increased cloud formation. Some researchers have proposed that passages through dense interstellar clouds may have triggered ice ages or mass extinction events. The evidence is not conclusive, but the possibility is unsettling.
In 2009, NASA launched a small spacecraft called IBEX. Its mission was straightforward: point its instruments toward the edge of the solar system and map what was out there. Nobody expected it to find something inexplicable, but that is exactly what happened. IBEX detected a massive ribbon of energy stretching across the sky. It had not been predicted by any model. It did not fit any existing theory. And after more than a decade of work, scientists still don't fully understand what it actually is. What we know is this: the ribbon shows up in data collected by instruments that detect energetic neutral atoms, particles formed when fast-moving ions from the solar wind collide with slower hydrogen atoms in interstellar space. The collision strips the ion of its charge and converts it into a neutral atom that can travel in a straight line without being deflected by magnetic fields. IBEX captures these atoms and traces them back to their origins. When scientists mapped the data, they expected to see a relatively uniform glow from all directions. Instead, they found a bright band cutting across the sky, spanning roughly 300 degrees and 2 to 3 times brighter than the surrounding regions. None of the models had predicted it. The ribbon appears to be aligned with the direction of the local interstellar magnetic field, suggesting the field is somehow focusing or amplifying the emissions in that particular region. But the exact mechanism remains unknown. One leading theory proposes that solar wind particles become trapped in the interstellar magnetic field. Rather than scattering randomly, they bounce back and forth along field lines, accumulating in a specific region. When they eventually neutralize and travel back toward the inner solar system, they produce the bright ribbon IBEX detects. But this explanation has problems. The brightness is higher than predicted, the edges of the shape are sharper than expected, and some features change over time in ways the theory cannot fully account for. What makes this discovery so unsettling is what it implies for our understanding of the local environment. We thought we knew the general structure of the space around us. We had decades of data from various spacecraft. We had sophisticated computer models. Then IBEX looked toward the edge of the solar system and found something entirely unexpected. This means our models are incomplete. The ribbon is not merely an interesting curiosity, it is evidence that something is happening at the boundary of our solar system that challenges our current understanding. If we don't understand the local interstellar environment, we cannot accurately predict what spacecraft will encounter as they travel outward. We cannot correctly model radiation exposure, and we cannot safely plan missions. The ribbon is a reminder that the universe does not care about our expectations.
We are not standing still. When you look at the night sky, the stars appear fixed and the darkness permanent, but everything is in motion. Our planet orbits our star. Our star travels in orbit around the center of the galaxy, and the entire solar system is drifting through a vast, invisible cloud of gas and dust. This cloud, called the Local Interstellar Cloud, is mildly radioactive. Roughly 30 light-years across, it contains thin hydrogen, helium, and trace amounts of heavier elements. The density is incredibly low, approximately 1 atom per 13 cubic centimeters. But across the vast distances of space, this amounts to a significant quantity of material, and our solar system is passing through it at roughly 80,000 kilometers per hour. Scientists estimate that our solar system entered this cloud within the last few thousand years. Before that, we were traveling through a far emptier region of space called the local bubble, a vast cavity formed by ancient supernova explosions. The transition from the empty bubble to the denser cloud has subtle effects on the heliosphere. The cloud's material presses against the edge of our solar system, providing the resistance that shapes the termination shock and heliopause, and contributing to the hydrogen wall building up at our nose. But here is the unsettling part. The cloud contains trace amounts of radioactive isotopes, atoms with unstable nuclei that release radiation as they decay. The amounts are small, and the danger to life on Earth is negligible, as we are shielded by the heliosphere, our planet's magnetic field, and its atmosphere. But the presence of these isotopes tells us something about the cloud's history. Radioactive elements in interstellar space typically come from supernova explosions. When a massive star dies and tears itself apart, it creates heavy elements through nuclear fusion and scatters them into space. Some of these are radioactive. Finding them in the local interstellar cloud means this material was enriched by stellar explosions in the relatively recent past. Scientists have detected some of these isotopes in deep ocean sediments on Earth. Iron-60, for example, is a radioactive form of iron that does not occur naturally on our planet. Finding it in the geological record suggests that particles from the local interstellar cloud have occasionally penetrated all our protective layers and reached the surface. This is not an immediate threat, the amounts are far too small, but it is a reminder that we are connected to the broader galactic environment in ways we tend to forget. The local interstellar cloud will not last forever. At our current speed, we will leave it behind within the next 10 to 20,000 years. Then we will enter whatever lies on the other side. It could be another cloud, it could be empty space, we don't yet know. What we do know is this: our passage through different interstellar environments affects the heliosphere. Denser regions compress the bubble, emptier regions allow it to expand. Over millions of years, these shifts can influence conditions in the outer solar system and potentially the inner planets as well. Whether we are aware of it or not, we are traveling, and the road ahead holds more surprises.
When Voyager 1 finally crossed into interstellar space, it entered a region that had been waiting for billions of years. The particles around it had not been created by our star, had not been born in our solar system. They had come from somewhere else, somewhere entirely different. And some of them are older than our planet. This is one of the deepest realizations of the Voyager mission. The moment the spacecraft crossed the heliopause, it began sampling material from the wider galaxy. And that material tells a story reaching back to the deaths of ancient stars. Interstellar space is not empty. When you picture the void between stars, you imagine absolute nothingness, a perfect vacuum, pure darkness. But the reality is more complex. There is matter out there, very little, just a few atoms per cubic centimeter. But across the vast distances between stars, those atoms accumulate into a significant quantity of material. The great majority of this material is hydrogen, the simplest element in existence, the building block from which everything is made. 9% is helium, the second simplest element. The remaining 1% contains traces of heavier things: carbon, oxygen, iron, silicon. Where did these heavier elements come from? They were forged inside stars. Billions of years ago, massive stars exhausted their nuclear fuel and collapsed. Some exploded as supernovae, scattering their interiors into space. Others shed their outer layers more gently, slowly releasing processed gas as expanding shells. Over time, this processed material mixed with the primordial hydrogen left over from the Big Bang, and today that mixture fills interstellar space. When Voyager 1 samples the particles around it, it is touching material that passed through stellar furnaces before our solar system had even formed. Some of these atoms may have been inside a star that exploded while dinosaurs still walked the Earth. Others may trace back to the earliest generation of stars in the galaxy.
This is not poetry, it is measurable science. Voyager 1 carries instruments capable of characterizing the composition of incoming particles. The data confirms that the interstellar medium contains what theory predicted: hydrogen, helium, and trace amounts of heavier elements in ratios consistent with billions of years of stellar processing. But there are anomalies as well. Some of the cosmic rays Voyager has detected carry energy suggesting they originated in extremely violent events, perhaps jets from distant black holes or shock waves from supernovae in other parts of the galaxy. These particles have been traveling for millions of years, bouncing off magnetic fields across one corner of space after another. When they finally arrive, they carry information about events we could never witness directly. In a sense, interstellar space is a library. The particles filling it are records of everything that has ever happened in the galaxy. Stellar explosions, black hole mergers, the slow deaths of red giants, the violent births of neutron stars. All of these events leave traces in the cosmic ray population and in the interstellar gas. Voyager 1 is reading that library, one particle at a time, decoding the history of our galaxy. And it is doing so entirely alone, farther from home than any human-made object has ever been. When Voyager 1 crossed into interstellar space, scientists expected the magnetic field to change. They were right, it did, but not in the way they had predicted. Inside the heliosphere, the magnetic field is governed by our star. The field lines spiral outward, bent by the star's rotation, pointing in a generally consistent direction. Scientists knew that once Voyager crossed the heliopause, it would encounter the interstellar magnetic field, which should be pointing in a different direction. The problem was that the direction Voyager measured did not match what the models had predicted. Based on observations of distant pulsars and other astronomical sources, the local interstellar magnetic field should be tilted at a specific angle to the plane of the galaxy.
When Voyager 1's magnetometer began reporting data from interstellar space, the field direction deviated from expectations. It had been rotated. This discrepancy sparked years of debate. One possibility is that our models of the local interstellar field are simply wrong. We had inferred the field direction from indirect measurements, and those measurements may contain errors. Voyager provides the first direct sampling, and direct data overrides indirect estimates. Another possibility is that the heliosphere itself is distorting the interstellar field. As our star pushes through the surrounding medium, its magnetic bubble may be bending the field lines and creating a transition zone where directions shift gradually. Voyager may be measuring this distorted region rather than the true, undisturbed interstellar field. A third possibility is that something more complex is going on. The interstellar medium is not uniform. It contains pockets of varying density, temperature, and magnetic character. Voyager may be passing through a local anomaly that does not represent the broader interstellar field.
Scientists are still analyzing the data. What makes this mystery so significant is what it reveals about our gaps in knowledge. We have been studying the galaxy for centuries. We have mapped magnetic fields across vast distances. We thought we understood the local environment reasonably well. Then a single spacecraft took a direct measurement and found something unexpected. The magnetic field is not merely a scientific curiosity. It shapes the movement of particles through space, influences cosmic ray propagation, and determines the structure of the heliosphere. If our understanding of the interstellar field is wrong, the models for all of these phenomena need to be revised. This is humbling. We sent Voyager to explore the edge of the solar system, and one of its most important discoveries was that we had the basic properties of our surroundings wrong. Not dramatically wrong, but significantly wrong. Wrong enough that scientists need to revise their assumptions. In 2003, astronomers discovered an object in a place it should not have been. Its name is Sedna, and its orbit makes no sense. Sedna is a chunk of rock and ice roughly 960 kilometers across. It travels around our star on an extraordinarily long path, at its closest point roughly 76 times the distance between Earth and our star, and at its furthest more than 900 times that distance. A full orbit takes approximately 11,000 years. The problem is this: Sedna never gets close enough to any known planet to have been nudged into this orbit. Jupiter regularly flings comets and asteroids onto unusual paths, and Neptune has shaped much of the Kuiper Belt by pushing icy bodies around. But Sedna's closest approach point lies far beyond Neptune's orbit. No known planet ever passes near enough to have influenced it. So how did it get there? Several theories have been proposed. One possibility is that Sedna was captured from another star. In the early days of the solar system's formation, our star was likely born in a cluster with other young stars, far closer together than they are today. A passing star may have brought Sedna with it, and as that star moved away, our star's gravity captured it. Another possibility is that there is an undiscovered large planet in the outer solar system. This hypothetical world, sometimes called Planet 9, may have gravitationally settled Sedna and similar objects into their current orbits. If Planet 9 exists, its gravitational influence could explain many surprising features of the outer solar system. A third possibility involves the gravitational influence of the galaxy itself. Over billions of years, the tidal forces of the Milky Way could gradually shift orbits in the outer solar system. Sedna may have been nudged onto its current path by these slow cumulative effects.
None of these theories has been confirmed. What we know for certain is this: Sedna exists, and its orbit points to something we have not yet found. Either there is a planet hiding in the dark, or our star has a more interesting history than we thought, or the galaxy itself is shaping the outer solar system in ways we are only beginning to understand.
Sedna is not alone. Astronomers have found other objects with similarly extreme orbits. Each one adds another layer to the mystery, and looming behind all of them is a larger possibility. There may be another unseen planet in our solar system. Not a small one, a world 5 to 10 times the mass of Earth, so far from our star that it has never been spotted. Its name is Planet 9, and the evidence for its existence is growing. Here is why scientists think it could be real. In the outer solar system, beyond Neptune, there's a collection of icy objects with extremely elongated orbits. These are called extreme trans-Neptunian objects. When astronomers charted their paths, they noticed something strange. The orbits were not randomly distributed. They were clustered and aligned in a way that suggested something was organizing them. Chance could not explain it. The probability was less than 1 in 10,000. Something had to be responsible. Computer simulations showed that a massive planet on a distant elliptical orbit could produce exactly this pattern. Its gravity would slowly pull the smaller objects, aligning their orbits over millions of years. The simulations predicted the approximate mass, distance, and orbital parameters such a planet would require. The numbers are striking. Planet 9, if it exists, may orbit at between 200 and 800 times the distance between Earth and our star. A full orbit would take 10,000 to 20,000 years. At that distance, it reflects almost no light, hidden from current telescopes without knowing precisely where to look. This is why it has not been found yet. Searching for Planet 9 is like finding a single dark grain of sand on a vast beach at night. The object is faint, moves slowly, and is lost among millions of stars and galaxies. Astronomers have dedicated significant telescope time to the search, but no confirmed detection has been made so far. Some scientists remain skeptical, suggesting the orbital clustering may be an observational bias arising from how we search for objects, rather than a real physical effect. Others propose alternative explanations that do not require an unseen planet. But the indirect evidence keeps accumulating. Beyond the orbital clustering, Planet 9 could explain other mysteries as well. The unusual tilt of our star's rotational axis, the existence of objects like Sedna, and certain features of the Kuiper Belt all fit the models better when a massive outer planet is added. If it is real, it would change our understanding of the solar system's history. Current theories predict that the solar system formed with 4 giant planets. A 5th giant would require them to be revised. The true edge of our solar system is not where most people think it is. Not at Pluto, not at the heliopause, not even at Sedna's orbit. The true edge lies roughly 100 times further out, in a region where objects take millions of years to complete a single orbit. This region is called the Oort cloud, and it is one of the most mysterious places in the solar system. We have never directly observed the cloud. No spacecraft has visited it. No telescope has imaged its contents. Everything we know comes from inference, from tracking the occasional comets that fall inward and tracing them back to their origins. What the evidence tells us is this: the Oort cloud is a vast spherical shell of icy objects surrounding our star. It begins at roughly 2,000 times the distance between Earth and our star, and extends perhaps as far as 100,000 times that distance. At its outermost boundary, our star's gravitational influence becomes comparable to the gravitational pull of passing stars and the galaxy itself. Scientists estimate the Oort cloud contains trillions of objects. Most are small, no more than a few kilometers across. They are made of ice and rock, flung outward by the gravity of the giant planets, frozen remnants left over from the formation of the solar system. They orbit our star, but barely. Their paths are so long and their movements so slow that they are almost drifting in the gravitational borderland between our star and the rest of the galaxy. The outer edge of the Oort cloud lies roughly 1 light-year from our star. The nearest star, Proxima Centauri, is approximately 4 light-years away. This means the Oort cloud extends a quarter of the way to our nearest stellar neighbor. For perspective, light takes about 8 minutes to travel from our star to Earth. It takes over a year to reach the outer boundary of the Oort cloud. Voyager 1, traveling at roughly 61,000 kilometers per hour, will not reach the inner boundary of the Oort cloud for another 300 years. Passing through it entirely will take another 30,000 years.
The Oort cloud is not merely distant, it is incomprehensibly vast and the source of the most dangerous visitors to the inner solar system. Long-period comets, appearing without warning on orbital periods of thousands or millions of years, come from the Oort cloud. Something knocks them off their stable paths: the gravitational pull of a passing star, the tidal forces of the galaxy, or random nudges from neighboring objects. Once deflected, they begin falling inward, gaining speed as they approach our star. Some of these comets pass harmlessly through the solar system and return to the outer darkness. Others strike planets. Over billions of years, Oort cloud comets have delivered water and organic molecules to the inner solar system. They have also caused extinction events. There is a slow-moving threat approaching from the dark. Every few 100,000 years, a star passes close enough to our solar system to disturb the Oort cloud. When this happens, billions of icy objects that have been drifting undisturbed for millions of years get nudged onto new orbits, and some of those orbits lead directly into the inner solar system. This is not speculation, it is measured science. Using data from the Gaia spacecraft, which has precisely mapped the positions and movements of over 1 billion stars in our galaxy, astronomers have determined which stars have passed close to our solar system in the past and which will do so in the future. The results are unsettling. On average, a star passes within 1 light-year of our star every 100,000 years. At that distance, its gravity is strong enough to disturb the outer Oort cloud. Closer passes are rarer but more dangerous. A star passing within half a light-year could send a significant number of comets falling inward. The effects are not immediate. Oort cloud objects move slowly. A comet deflected today might take 1 million years to reach the inner solar system. But on geological timescales, these disturbances accumulate. The rate of comet impacts on Earth fluctuates over millions of years, and some researchers believe these fluctuations are linked to stellar passages. This may have profound consequences for life on our planet. The mass extinctions in Earth's history show a rough periodicity of approximately 26 to 30 million years. Some scientists have proposed that this periodicity may be connected to the movement of our solar system through the galaxy, which causes periodic increases in stellar encounters and Oort cloud disturbances. The theory is contested and the evidence incomplete, but the underlying physics is sound. Passing stars disturb the Oort cloud, deflected comets fall inward, and some of them strike planets. The dinosaurs were wiped out 66 million years ago by an asteroid or comet impact.
That object came from somewhere. Millions of years before it struck Earth, it is possible that a stellar encounter nudged it onto that trajectory. We cannot stop this process. Stars travel their own paths, and the galaxy does not care about our survival. But we can monitor it. We can track nearby stars, detect inward-bound objects far enough in advance to attempt deflection. This is why mapping the outer solar system matters. The better we understand the Oort cloud and its dynamics, the better we can anticipate and prepare for future threats. The danger is real, but slow. Any given generation faces vanishingly small odds of experiencing a major Oort cloud comet impact, But over millions of years, that probability becomes certainty. Something will come. The only question is when. Not all planets orbit stars. Some drift alone through the galaxy, wandering through the darkness between stellar neighborhoods with no system to call home. These are called rogue planets, and astronomers believe they outnumber stars in the Milky Way. The Standard Model said planets needed a star to exist. Then observations began challenging that assumption. Increasingly smaller objects were detected, some clearly of planetary mass, too small to ever become stars. The current estimate is striking. There may be billions, perhaps trillions of rogue planets in our galaxy alone. Most probably formed normally around stars and were then ejected through gravitational interactions. Others may have formed independently, collapsing directly from gas clouds without ever belonging to a star system. Why does this matter for the outer solar system? If rogue planets are common, the probability that one has passed close to or through our solar system over billions of years cannot be dismissed. Such an encounter could be catastrophic. A planetary mass object passing through the Kuiper Belt or Oort cloud would scatter everything in its path, potentially sending a wave of debris toward the inner solar system. Even a distant pass could cause problems. Gravitational disturbances from a rogue planet could destabilize orbits and shift the positions of outer solar system objects. Could one be passing through the outer solar system right now without our knowledge? It is possible. Rogue planets are extraordinarily difficult to detect. They emit almost no light and are invisible in reflected light since they have no star to reflect. The only ways to find them are through their gravitational effects or occasionally the faint infrared glow of their residual heat. Current surveys are not sensitive enough to detect most rogue planets.
A star is coming. Its name is Gliese 710, and it is currently about 64 light-years away. That sounds like a safe distance. It is not heading directly toward us and will not collide with our star. But in approximately 1.3 million years, it will pass within 10,000 astronomical units of our star, placing it squarely inside the outer Oort cloud. That is close enough to cause serious disturbance. Gliese 710 is a red dwarf with about 60% of our star's mass. As it passes through the Oort cloud, its gravity will sweep through trillions of icy objects like a hand plunged into a container of sand. Some will be flung outward, ejected from the solar system entirely. Others will be pushed inward, their orbits altered enough to send them falling toward the inner planets. Computer simulations predict the encounter could increase the number of comets entering the inner solar system by several times. This elevated comet flux will persist for millions of years as the disturbed objects slowly drift sunward. But here's the good news. 1 million years is a long time. Human civilization is only a few thousand years old. The technology we have developed in the last 100 years would look like magic to someone living a century ago. What we might be capable of in 1 million years is entirely beyond our imagination. If humanity survives that long and continues advancing technologically, we will almost certainly have the capacity to detect and deflect incoming objects. The threat is real, but manageable, a problem for our distant descendants, not for us. Yet this encounter is a reminder that the solar system is not a closed environment. We share the galaxy with hundreds of billions of other stars, all traveling their own paths, all capable of affecting us if they pass close enough. For decades, something was pulling our spacecraft backward. The effect was too small to measure precisely, but it was real, and for years nobody could explain it. The mystery began with Pioneer 10 and Pioneer 11, launched in the early 1970s to explore Jupiter and Saturn. After completing their primary missions, they continued traveling outward, becoming the first human-made objects to journey toward the edge of the solar system. Engineers on Earth, tracking their positions with extraordinary precision, noticed something strange. Both Pioneers were slowing down slightly more than they should have been. The deceleration was tiny, an acceleration of about 1/1000th of a meter per second. But over years and billions of kilometers, it accumulated into a significant discrepancy. Pioneer 10 was roughly 400,000 kilometers behind where gravitational calculations said it should be. Something was wrong.
Scientists accounted for every known force: the gravity of the planets, the pressure of sunlight, the friction of interplanetary dust. Nothing could explain the discrepancy. For over 30 years, the Pioneer anomaly remained one of the great mysteries of space science. Some researchers proposed exotic explanations. Perhaps gravity worked differently over large distances. Perhaps dark matter was somehow involved. So what was the answer? In 2012, a team of scientists solved the mystery. The answer was not exotic, it was thermal. The Pioneer spacecraft ran on plutonium, and radioactive decay produced heat as a byproduct. This heat radiated from the spacecraft in all directions, but due to the design, slightly more heat was emitted from the front than from the back. Heat carries energy, and energy carries momentum. When more photons are emitted from the front than the back, a small push is created in the opposite direction. The effect was tiny, but it matched the observed anomaly almost exactly. The mystery was solved. This outcome might seem like a disappointment, but the Pioneer anomaly taught us something important. At the edge of the solar system, even the smallest forces matter. Thermal radiation, gas leaks, even the momentum of radio signals can affect a trajectory. When Voyager 1 sends a signal home, almost a full day passes before anyone hears it. Light itself, the fastest thing in the universe, takes over 22 hours to travel from the spacecraft to Earth. A round-trip communication takes nearly 2 days. Voyager 1 is currently more than 24 billion kilometers from Earth. If you drove there at highway speed without stopping, it would take over 25 million years to arrive. The signals the spacecraft sends are unimaginably faint.
It transmits at roughly 23 watts, the same as a refrigerator light bulb. By the time that signal has traveled 24 billion kilometers, the energy reaching Earth is measured in billions of a watt. Detecting it requires the largest radio telescopes on the planet. The Voyager's power sources are running out. Both run on radioisotope thermoelectric generators that produce electricity from the decay of plutonium. At launch, they generated around 470 watts. Today, they produce less than half that. NASA engineers have had to conserve power for the most critical systems, shutting down heaters and disabling backup systems. The spacecraft are slowly growing cold. By the early 2030s, there may not be enough power left to run any instruments. The Voyagers will fade into silence. Every piece of data they send before that moment is precious. Every signal carrying information about a region of space that no human will visit for centuries, perhaps millennia. From where Voyager 1 now drifts, our star is just a bright point of light. Not a disk, not a blazing presence filling the horizon, just a dot. Brighter than other stars, but still just a dot. You could cover it with your thumbnail at arm's length. In the famous pale blue dot photograph, taken when the spacecraft was about 4 billion kilometers from Earth, our planet appeared smaller than a single pixel. Voyager is now nearly 4 times further away than where that photograph was taken. If its cameras could be turned, which they cannot, having been shut down years ago to conserve power, Earth would be invisible, lost in the glare of a star that is itself just a point of light.
At the outermost reaches of the outer solar system, our star begins to lose its dominance. Near the outer boundary of the Oort cloud, roughly 1 light-year away, our star's gravitational pull becomes comparable to the cumulative gravitational influence of the Milky Way galaxy.
Objects there feel two competing tugs, one from our star, weakened by vast distances but still present, and one from the imperceptible pull of the galaxy, the combined mass of everything from here to the galactic center. This galactic tide, over millions of years, reshapes the orbits of the outer Oort cloud in strange ways, flinging objects out of the plane of the solar system and nudging them from stable paths onto new trajectories that eventually send them falling inward. Some researchers believe the galactic tide is one of the primary mechanisms responsible for sending long-period comets into the inner solar system. The greatest tools we have for understanding these mysterious boundaries are still two spacecraft, Voyager 1 and Voyager 2. They were built with 1970s technology, their systems more primitive than a modern smartphone, yet they have endured radiation, temperature extremes, and nearly 50 years of continuous operation. Every measurement is a triumph, every signal a whisper reaching us from billions of kilometers away. And if you could listen to interstellar space, you would hear a hum, faint, constant, arriving equally from every direction, having traveled toward you for nearly 14 billion years. This is the cosmic microwave background, the residual glow of the Big Bang. As the universe expanded, the wavelengths of that first light stretched and shifted into the microwave spectrum, but it still fills every corner of space, from every direction. Voyager is now immersed in this ancient radiation, surrounded by photons emitted by the first atoms that ever existed, billions of years before our world was born. The edge of the solar system is not an ending, it is a threshold. Everything we have ever known, the planets, the comets, the world that harbors life, all of it fits inside this fragile bubble our star has created. And beyond that bubble lies the galaxy, the vast structure that has been shaping us for billions of years, reshaping us a little more each day, and will ultimately reclaim us all. The Voyagers showed us not just space, but our own smallness. And perhaps that is one of the most important things there is to discover. Good night.